So now, when we saw limits of sequences, we only saw limits, when n goes to infinity, and there's only one way you can approach infinity, right? So if plus infinity, so all of it, the right, we go always from the left, right? But if we're seeing the limit of this function at a point A, we can go from the left and we can go from the right, right? From sequences that, if you think about the definition in terms of sequences, we can approach A with a sequence that's below A, or we can approach A by a sequence that's above A, right? So now we have this, we use these two definitions to make this distinction clear, right? We call it one-sided limits. So we say that the left-handed limit of a function f when x approaches A is L, and denote that the limit, when x goes to A from the left, if for every epsilon there exists a delta greater than 0, such that the difference between f and L is smaller than epsilon, whenever, and then we have our x is between A and A minus delta. So this is A and A minus delta. So instead of considering the whole interval between A minus delta and A plus delta, as we said before, we're only considering values from below. And the same thing with the right-handed limit, but from above, right? So you could think about, for instance, the Heaviside function, okay? The Heaviside function, which is defined like this: h of x is 0 when x is smaller than 0, and it's 1 when x is greater than 0, okay? Now the limit when x goes to 0 from the left of h of x is clearly 0, right? And the limit when x approaches 0 from the right is clearly 1, right? So this function is this, it has this value, right? And then, well, it takes this value, right? So this is h of x. It's also called the step function, okay? Because it takes a step at 0. Now, so we have two different limits, one-sided limits at 0. So this means that the limit at 0, okay, as we have seen, doesn't exist, because if we take a sequence that approaches 0 from the left, from the right, the limit will be 1. If you take a sequence that approaches 0 from the left, it will be 0, okay? So that means that the limit when x goes to 0 of h of x does not exist, okay? But this is not only true for this function x, this is general, okay? So in order for the limit when x goes to A of f of x to exist, okay, we have to have, and this is an equivalence, it's easy to prove, we have to have that the limit from the left and the limit from the right are equal and equal to L, okay? Now, sometimes, as we saw with sequences, right, when you're approaching infinity, the limit is not convergent, okay? With functions, we have something like this. We approach a value A, and the function keeps increasing, and it doesn't converge to any finite value, okay? So we say that the limit of a function f when x approaches A is plus infinity or minus infinity, okay? And denote it like this: limit when x goes to A is plus infinity, minus infinity, if for every n that's greater than 0, and or smaller than 0 if we're thinking about the negative infinity, there exists a greater than 0 delta, such that the value of the function is greater than m, or smaller than m if we're thinking about the negative infinity, whenever x minus a is between 0 and delta. Okay, so think about this function, okay? This is just thinking that it doesn't matter how close we get to A, we can always find a value that's closer and that's greater than any bound that we think, okay? So this function, 1 over the absolute value of x, let's prove that the limit when x goes to 0 of 1 over the absolute value of x is plus infinity, okay? So suppose we have any m greater than 0, okay, and we want to compute, we take any, are we able to find a delta, right, that so that x is between 0 and delta, such that 1 over x is greater than m, okay, which is what we want, okay. This is what the definition asks us, right? Are we able to find a delta like that? Yes, because we can take delta smaller than 1 over m, right? Sorry. So if delta is smaller than 1 over m, that means that 1 over x is going to be greater than m for every x in this interval, right? And it doesn't matter how high we pick m, because we can always choose a delta that's smaller than 1 over m. So that means that the function is unbounded in this when it goes to 0. That means that the limit is going to be plus infinity, okay? Using the same argument, we can prove that the function f equals 1 over x has a left-handed limit, okay, from the left to be minus infinity, okay? And again, because if we choose whatever m smaller than 0, we can choose a delta, let's see, it's a delta, and it has to be greater than 0, okay? So let's choose it like this, right? So if m is smaller than 0, delta is smaller than 1 over minus m. This implies that 1 over m is smaller than minus delta, which is smaller than x, smaller than 0, okay? And this implies that 1 over x is smaller than m, okay? So it's the same thing like before, but here instead of considering x between 0 and delta, it's x has to be between minus delta and 0, okay, because this is the left-handed limit, okay? So we know that the limit when x goes to 0 from the left is minus infinity. We can prove easily that the limit when x goes to 0 from the right is plus infinity. So that means that this function doesn't have a limit, and that's what I just plotted before, that this function does something like this, okay? It goes to minus infinity from the left, it goes to plus infinity on the right, okay? Now we have a special limit that when a is plus or minus infinity, which is very similar to the limit of sequences that we saw before, we say that the limit of a function f when x approaches plus or minus infinity is L, and denoted the limit when x goes to plus or minus infinity, what is like this: if for every epsilon greater than 0 there exists m greater than 0 or negative than 0 if we're thinking about the negative infinity, such that the difference between f and the limit is smaller than 0 whenever x is greater than m, okay? So for instance, let's think it's the same. It may be, you know, kind of abstract to think about this in these terms, but just think about, you know, how functions behave when they are x is going to infinity, you know. That means that we can get values m as large as we want, and we can get closer and closer to L. So let's see that the limit when x is going to plus infinity of 1 over x is going to be 0, right? So suppose we have any epsilon, we want to take any epsilon, and the idea is, can we find an m such that for x greater than m we will have so x will be 0 between 1 over x 1 over m, right, such that x 1 over x minus 0 is smaller than epsilon, okay? That's what we need. Can we find an m such that this is true? Well, if you think about it, if what we want is this, we can think that 1 over m has to be smaller than epsilon, which means that m has to be greater than 1 over epsilon, okay? Similar like that we did before, right? So if we take any epsilon, we say, well, if m is greater than 1 over epsilon, then any value x that's greater than this m will have this property, okay, that the difference between 1 over x and 0 is smaller than epsilon, okay, and you can substitute some values for epsilon and m if it's clear for you, but this actually fulfills the definition, okay. So yeah, I think that's it for this video, and in the next one we'll see some algebraic properties of limits.